We understood that in the first generation of computers, like there were vacuum tubes. Uh, so there were no monitors, and the speed of the computer is in milliseconds. So it is like 10 power minus 3 of a second. And there were a lot of performance issues in the first generation, and then the technology was a little bit slow and all that. Now, coming to the second generation, so that this was like from 1956 to 1963, we call this the second generation of the computers, where like the vacuum tubes have been replaced with the transistors. Okay, so what is a transistor? So you can see a transistor over here. So as I said, like it is a very, very tiny component, electronic component, which will be not even 1 inch. Okay, so if you just put in your palm, it will not even occupy 1 inch of the space on your palm. So it's very small and very reliable and energy efficient component. So if you just try to understand what is a transistor is a switch, like, okay, just like how vacuum tubes are, even transistors were like that. So what is a switch? We know that in an electric circuit, a switch is something which controls the flow of electricity. This transistor will be controlling the flow of electricity, and then it also amplifies the signal. This is made up of semiconductor material. Mostly it is a silicon type. Okay, right. So transistors are generally used in computers, then in phones and TVs, and almost in all the digital components that we are seeing today, we have transistors. Okay, even today, like the transistors era is going on from the second generation. So the transistors make up the logic gates. What is a logic gate? Logic gate is like a computational part of your computer where it tries to do the logical and numerical type of calculation. So all that are done by the transistors. Okay, so this is the technology that we have been using from the second generation. And then if you just look at the memory, memory is nothing but your RAM. So what is RAM? RAM is random access memory. Okay, so the random access memory is the magnetic core memory. So which is your random access memory. So random access memory is also considered to be the primary memory. So any operation that you are going to do will be happening in the primary memory only. So this magnetic core memory is faster than the magnetic drums. Okay, so in the magnetic drum, you will be having a spinning drum. So what is one of the major differences between magnetic drum and magnetic core memory is that, so suddenly say that there is a power off when you're using the first generation computer, say if suddenly there is a power off. And when there is a power off, then whatever is there in the RAM, like the data is lost. But if you're using magnetic core memory, so even if the power is lost, it will be having a capability to retain whatever it was doing before the power off. So static memory, static magnetic core is used over here, and there is no moving part over here like the drum and all. So that is regarding your memory. Now coming to the storage, storage is nothing but your ROM, which is read-only memory. So which is the secondary storage part of your computer. So where like, can you tell me what were used in the previous generation? In the first generation, what is the storage? What is the
Punch
storage in the,
cards.
yeah, punch
Punch,
cards?
Punch
punch
Yes.
cards.
books. Yeah.
Yeah, punch cards. Okay, fine. So the difference over here is like, which is better? Of course, magnetic tape and magnetic discs are advanced to the punch cards. Because like there is random access here with the magnetic discs over here. Like it is like if you want to watch a movie from the beginning till the end without jumping from one place to another, then it is considered to be sequential access. But say, for example, you liked a part of a movie and you directly wanted to go to 15th minute of a movie and all that, that is called as a jump. Okay, so which is considered to be random access. So with the punch cards and all, random access is not possible. But with the magnetic disks, the random access is possible. Even with the magnetic tapes, random access is not possible. But magnetic disks are even more advanced compared to the punch cards and the magnetic tapes. Okay, right. This is regarding your storage. So there have been certain advancement in the technology and in the memory and also in the storage in the second generation. And as you can see that the capacity is also 1000 kbs. Okay, right. So it has moved from kilobytes to megabytes. Okay, so like now what is data size table. I already have shown you. So like where 1024 KB is equal to 1 MB. So the capacity of the computer's storage capacity and the random access capacity and also having increased from kilobytes to megabytes. And next, coming to one of the very, very important topics, which is like the language used. Okay, so it is machine
Okay.
language, which is like made up of zeros and ones, right? So which is a binary language. And for doing any operation, the programmers have to calculate the binary code for the operations and then give that as an input to the computer. But it was not at all human friendly. Okay, so whenever you want to write a program, it was on the burden, it was on the head of the programmers to actually calculate the binary code and then give that, punch holes in the punch cards and then give that as a feed into the computer. So it was very, very tedious. In case if there is an error in the code, again, it was very difficult for them to rectify because again, they have to punch holes in the punch cards and then give that as a feed into the computer. So assembly language is considered to be low level language where like there will be mnemonics. Okay, so which is considered to be mnemonic language. What does it mean by mnemonics? Okay, so mnemonics are nothing but human readable shortcuts or symbols. So I'm repeating again, mnemonics are human readable shortcuts or symbols that are used over here. So say for example, to add two numbers, instead of giving it in binary, I'll say simply add. So human readable things. Okay. So say I want to move the data from one register to another register. So I'll say MOV. Okay. So say for example, I want to do subtraction. I'll be giving it as SUB. Or say I want to do multiplication. So I'll say MUL. So there are certain mnemonics over here. So it's very easy for the programmers because they combined this machine binary code along with some mnemonics, which are like human readable things, so which made their life a little bit easy. I'll again show you like what is assembly language, comparison between assembly language and the machine language in the next slide. Before that, we'll see what the next point of comparison between the first generation and second generation. So which is like microseconds per operation. Okay, so any operation that you take. So say, for example, I want to add two numbers. So this is the operation I want to do. Okay, right. So when I say like in the first generation computer, so it is milliseconds, right? So it is 10 power 3 of a second. But in the second generation, so what happened is the time taken for the same operation is 10 power minus 1 minus 6 of a second. So which is faster? Of course, 10 power minus 6 of a second is much faster. Okay, right? So the speed of the computers also have increased a lot. So next is size. Okay, so how much smaller? Okay, so here we are discussing about the size of the computer. So the size of the computer is much smaller and more portable compared to the first generation. As I have quoted in the first generation slide, that the size of the computer is as big as the size of a room. Okay, but what happened in the second generation is because of the transistors. So the circuits all have scaled down. To a little bit miniature kind of circuits have started coming up. And then the size of the computer also have shrunk compared to what it was in the first generation computer. Okay, right. And next one is the second generation computer was when the basic operating system. So if you just see in the first generation, there was no OS. OS is nothing but operating system. Operating system acts like a mediator between the user and the hardware. So what happens over here is like we do have the hardware. and we do have the user who wants to perform certain tasks. So say, for example, the user wants to play a game. Okay, so if user wants to play a game, so he have to give certain instructions, and the instructions have to be executed by the hardware, and then the result has to come to the user. So we need a mediator in the middle who works in between this hardware and software. Okay, so in between this hardware and software, we need a mediator, and that mediator is nothing but the operating system. So today we see a lot of operating systems. We see Microsoft. Okay, so MS is a operating system. Unix is an operating system. Then you can see Mac OS is an operating system. Okay, so then we see Macintosh. Okay, so then all these are Linux is an operating system. So all these are operating systems that we have. So operating systems also started evolving. So it started taking a shape from the second generation computer. And examples of the computers that were in the second generation computers are IBM 1401 and then CDC 1604. So all these are examples of the second generation computers, and these computers are kept in the museum. Okay, so in the computer, there's a computer museums where all these first generation, second generation, third generation computers have been kept for display for the users to see, like how computers were in the beginning days and today how the computers are, like palm size, and then just you can see your fitness watches where the computations are happening just in 1 inch of a circuit. Okay, so I just tried to put up a comparison for you so that you'll understand how the languages have evolved. So at the right extreme, you can see machine code, okay, so which is binary code for the same operation. So for the same operation of adding two numbers, okay, so I just wanted to add two numbers, which is A and B, where A is holding 5 and B is holding 3, and I want the result of this, okay. So I just wanted to do a summation of these two numbers, okay, right. So if you just look at the right extreme, so everything is binary. Okay, you can see, and it is completely not understood by a human. Okay, so if I just show it to somebody who is a non-programmer, they won't be able to understand a bit of it. Okay, so everything is numerical, every operation. So say, for example, this is considered to be like the register, and this is considered to be the number. So of course, this is 5 over here, and this is 3. Okay, so this is number. And what is this? This is nothing but the opcode. Opcode is nothing but the mnemonic that I talked about, like which is the binary code for move AX. Okay, and this is the binary code for move BX, and this is the binary code for adding all this and so on. So you can see that the binary code over here is very difficult for any humans to understand. So it is very difficult for humans to understand. So then came the assembly language. Okay. So if we just look at the assembly language, so it is a little bit easy for humans to understand. So that's why we call it as the low level language. Okay, so low level language, where I'm saying move is the mnemonic, and I'm saying AX. What is AX? AX is the register. Okay, so inside your computer, there will be registers which are used for storing the data. So what is register for? Register used for storing the data. So it is used for storing the data. So I'm asking the computer. So I'm giving an instruction over here. So what is this? This is an instruction. So this is like a command I'm giving to the computer that move 5. Okay, so 5, move 5 into the register which is named as AX. That is this command. Okay, so what is the command over here? The command is like move, okay, 5 number into the register AX. Okay, so that is what I mentioned over here. And the syntax is very, very important. I should not be writing it in any other way other than this. Okay, right. And then I'm saying load B. Okay, so first one is load A. For load A, this is the instruction I'm writing. And for loading B, I'm writing this instruction wherein I'm saying move, okay, number 3 into the register, which is BX. Okay, so now both the data are in the register. So now I want to perform the addition of the two numbers. So I'm saying add. So here move move, add, or move, all these are the mnemonics in the assembly language. So I'm saying add the numbers that are there in both the registers, in AX and BX. So add these both. Now what happens with the add over here is, it will be adding the numbers in AX and BX and put the result in AX itself. Okay, so the result will be in AX. So say for example, the operation will be like AX is equal to AX plus BX. Okay, AX plus BX. So what is there in AX? The operation on the right side will happen first. So what is there in right side? AX is there. So what is the data in AX? 5 plus what is the data in BX, which is 3. So it performs the operation, so which is 8. And then this 8 is moved into whatever is there on the left side. So which is AX. So this operation, what it will do is, it will perform the operation and put the result in AX. So now where is the result? The result is in AX. So what we're doing, we are moving the result from the register AX to register CX. That's what we have done. So I'm storing the result in C. So which is like moving the result from AX register to CX register. So this is a little bit understood by the humans. Okay, so we can understand. But the point over here is, can a machine understand? So can your computer understand whatever you have written here in the assembly language? Can your computer understand? No, computer cannot understand. Then what extra do you need over here? Okay, so if writing in assembly language will only benefit the programmer, will only benefit the programmer. The life of the programmer became a little bit easy, but machine or your computer will not understand this assembly language. It will not understand this machine language. So what we need over here is, we need a translator. So we need a translator. So what is the purpose of the translator? Is that you are writing the code in assembly language, and the code that you have written in assembly language will be translated into this machine language. Ultimately, listen to me very carefully. Ultimately, your whatever code that you're writing in assembly, your machine will not understand. Ultimately, it only need the code that is written in machine code. It only understands the language of the machine code. It will not understand your C program, your assembly program, your Java program, nothing it understands. It only understands ones and zeros. So, but then why we have assembly language? As I already said you, that assembly language is only to make the life of the programmers easy. Only to make the life of the programmers easy, the languages have evolved. So writing in assembly, you need a translator which will convert the assembly level language into the machine language. So what is that translator? The translator is nothing but assembler. Assembler. The assembler is nothing but a program, or which is a software which will convert the assembly level language into the machine code. Okay, so that is the purpose of your assembler. So from the second generation computers onwards, like the assembler have come into the picture. In the first generation, you don't need an assembler, because whatever you're writing in machine. Whatever the computer understands, you're writing in that way. So there is no need for a translator. Whatever you're seeing over here, like this high level language, which is a C program. Okay, so you can see C program is like very easy over here to understand. Like this is completely human understandable. So I'm just saying int, which is considered to be integer. So I'm saying 5 is an integer. So everybody know what is an integer. When a number don't have a decimal point. So say, for example, I have 5.2. 5.2 is not an integer. Not an integer. What is an integer? Integer is a whole number. So it could be 5 or 100 or 200 or 300, 305 or whatever. When I have 5.25 or 7.85, so then the data type over here is nothing but a float. Okay, so I'll be taking a float and then work on it. So here I'm mentioning like what type of data I require, and I'm saying it's an integer, which means that it is a whole number. Okay, so I'm saying it's a whole number, and I'm saying a is equal to 5. Okay, so then I'm saying I have one more integer, and that is b is equal to 3. Then I'm saying add a plus b, and then put the result in C. That's it. Very, very easy for you. So the code over here, whatever I have shown you over here is C program. Okay, so the same can be also can be viewed as this can also, because we don't have a printf and scanfs and all that. So this high level language, it could be written in C or Java or whatever, but this is how we write in the high level languages. Okay, so which is like very easy. Like imagine writing your program in machine code and imagine your code writing in high level. So of course, high level programming language is more easy on the programmers. Okay. So as I gave you an example of this one, like which is IBM 1401 in the second generation computer. So I tried to put up a picture from the Museum of Computers. Okay, so this is the picture of IBM where there is no monitor. So you can see that this is the computer. Okay, so this entire part over here is the computer. So which is put up in the museum over there. So there is no monitor here. So you can see no monitor. And whatever you have to do, you will be doing over here, feeding the data into it and all this. So the tapes that you are seeing over here. So I talked about the magnetic tapes and all. These and all are the storage that you can see. So the computer is like, even here, the computer is like the room size, but not so big like in the first generation computer.